All right, so welcome to a topic that's not quite pre-cal, but it's kind of covers some IB material, and it's a good break before we go on to winter break. It's counting. So counting is very important on when you multiply and when you add. So there is this thing called the basic counting principle that says that however many things that you have uh, for each option or something like that, you multiply those numbers. So, like for example, this first question here, how many ways can six students arrange themselves in a line? So I like to be visual, so I drew six blanks because it's very important in this line that there's a first person and there's a last person. So there's a very specific place for these people to go. So if you think about, okay, well, if you have this group of six students and you want to put one first in line, there are six different ways of putting a student in that spot. Well, once you put a student in that spot, there's only five students left. So that means there's five different ways that you can put a student second, and four for the third, and three, two, and then the last person, there's only one person that could go last. So that's what that is. So these are all the different possibilities that we have for each spot. So what we do, the basic counting principle says that I just multiply all those numbers. Now, what if those numbers are really, really big? We don't want to multiply like 60 times 59 times 58 times 57 all the way down to 1. So in math, we have this thing called a factorial. It's like an exclamation mark in English, but a factorial. If you look at the box underneath, it talks about how n factorial is just n times n minus 1 because you take one away from the previous one, two away from the first one, it gives you the next number, and so on and so forth until you get down to 1. So let's see how well this transitions on here. Oh, sweet. So here is the calculator. So I'm going to be telling you a lot about going to alpha and then window. So in the newer fancy calculators, you can see that factorial is down here at the bottom. If you kind of glance on what's next on our paper, we have NPR and NCR as well. So when I say go to alpha window, that's what I'm talking about. If you don't have this menu, you can go to math, then scroll over to probability, and that's where all three of those are. So in the newer calculators, alpha window is going to be the easiest way to get there. So how do I, and then so if you type in 6 factorial into the calculator, you end up getting that there are 720 different ways of aligning six students in a group or in a line. But what happens if you don't use all the students? What if, like on this next one, we have 30 students and we want to put them in very specific offices in a club, and there's 4 offices. So if you just decide like, hey, let's fill in the president first. There are 30 students that can be president right now because nobody's given an office. But one person can't hold multiple offices, so that means once one student's president, there's only 29 that can be vice president, 28 to be secretary, and 27 to be treasurer. So again, with these kind of things, I like to be visual. If I'm asking you to write a certain digit, like a certain number that has like 4 digits, draw 4 blanks and try to figure out how many go in each one of those. And again, all I'm going to do is multiply those. So in the calculator, if you put that in there, you get 657,720 different ways of assigning 30 students for specific offices. Now, again, what if these numbers get really big? You don't want to do that for all of them. So how can you do this? Well, we call these permutations, where n is the number of items I'm choosing from, and r is the number of items I want. So in this case, I can use permutations and say that it's 30p4. You can put that into the calculator, go to alpha window, choose NPR, and plug in 30 and 4. If you don't have a newer calculator, come by and see me before you go buy one or something like that. Just come and talk to me, and I can show you how the older calculators kind of work with this. So how do you know if it's a permutation? Well, I like to say that permutations are precise because they both start with the P. That means that you have to put things in very specific spots, just like the first question. You can also do 6p6 if you want to, because you have 6 students to choose from. You want to put them in 6 specific spots in a line. So that's also a permutation. Here we're putting them in specific offices, so it's very precise. So order matters. So if you think about this problem, if you were to take these same 4 students and assign them a different office, that would be a totally different committee. So the order matters there. What if I give you a problem where I'm only taking 20 students and I want to make a group of 4? I'm not assigning them very specific jobs. So what you would do here is you would think about, okay, well, we had 20 students to choose first, then 19, then 18, then 17. However, if I choose students 1, 2, 3, 4, that's the same group if I chose students 4, 3, 2, 1, if I had labeled all the students 1 through 20. So what I could do is I can get rid of all of that repetition by dividing by 4 factorial. Because if I have those 4 students, there's 4 different ways of reorganizing those, or 4 factorial different ways of reorganizing those 4 students. Or there's a formula that's already made for us for combinations. So in this problem, I have 20 students to choose from, and I want 4 of them. So if you want to put that in a calculator, you can do that. Just covering some notation, you might see something that looks like this later on down the road. That's also the same notation as 20C4. So if you put this in the calculator, you end up getting that there are 4,845 different ways to choose 4 students from a group of 20. So it's very important to understand that order does not matter with combinations. Where permutations are very important on where you're putting those students or where you're putting things at. It's very precise, very specific. If it doesn't matter, if it's very general, it's a combination. Again, with these, it takes practice to understand. So like, for example, how many triangles can be formed from 10 points on a triangle? Well, let's just say like if I had 3 points, that creates a triangle. If I were to connect this point to this point, and then this point to that point, and then this point to that point, that's a triangle. But what if I go from this point to that point, and then this point to that point, and then this point back to that point? Well, it's the same triangle. So order doesn't matter on how I connect these 3 points. So this would end up being a combination where I'm choosing from 10 points, and I only want 3 of them. So put that in the calculator, and you end up getting 120. What's another situation where I can use combinations? Well, this next question, we have a salad bar that contains 9 different foods. How many ways can 7 or more foods be selected? So I need to think about, okay, well, 7 or more foods be selected. That means I choose exactly 7 items, exactly 8 items, or I can choose all 9 items. There's no way of doing 10. So if I do that, well, let's think about it. Does it matter the order that I put things on my plate? Like if I put salad, then croutons and cheese, is that a different salad than putting croutons and cheese and salad? No, that's the exact same thing. So order doesn't matter. You might be judged a little bit if you put your salad as croutons first and then cheese and then, the lettuce after that. But in this right now, you're not being judged. It's a completely similar dish. So since the order doesn't matter, I have 9 items to choose from, and I want 7 of them. There's 9 items to choose from, and I want exactly 8 of them. And then if I want to choose all 9. Then this is the hard part. Do I multiply or do I add? That's going to be the hard part about this unit. So you have to ask yourself, can I do all of this at one time? Can I go up to the salad bar and get exactly 7 items, and exactly 8 items, and exactly 9 items? No. You have to go 3 different times to get 7, exactly 8, and exactly 9. So since these are 3 separate events, we're going to add each of those events. Within the problem, there's a lot of multiplying, but since I can't do all 3 events at the same time, I need to add them. So 36 ways for this, 9 for this, and 1 for that, to give you a total of 46 different ways to choose something from a salad bar and get at least 7 items. What if you have the word party, like the letters in the word party, and you want to reorganize them? Well, again, this is kind of like a student problem. We want to use all 5 letters. So I asked myself, okay, well, how many letters could go first, second, third, fourth, and fifth? And since it's the basic counting principle, I just multiply them all. So you end up getting the same thing as 5 factorial or 120. What about the word dismiss? Well, there's 7 letters, 7 spots to put those letters, so 7 factorial. However, there's some repeating letters. So let's just say if I change those last 2 S's, is that any different than the previous word? What if I choose those I's and switch those? Those are all the same word. So how do I get rid of the overcounting? Well, I'm going to divide by, well, since there's 2 I's and there's going to be 2 factorial different ways of reorganize them, there are 3 S's, so I'm going to do 3 factorial ways of doing that. So be very careful how you put this into the calculator. You should get 420. So practice that and make sure you can do that. What if we're putting 3 boys, 5 girls, and 2 dogs all in a line and make sure, and like they're taking a photo or something? Well, to organize the boys and they all have to sit together, that would be 3 factorial different ways. There's 5 girls, so 5 factorial, and then 2 dogs, so 2 factorial. That's how many ways you can reorganize them if they have to sit together. So you have to ask yourself the question, is this one event or 3 different events? Well, let's just say if you're taking a photo with all of these people, you want them all to be in one picture. So this is going to be one event. So you're going to multiply them all. However, the only thing it says is that they all must sit together. So you have to think, okay, well, is it the same thing if I put girls then boys and dogs, or dogs then boys and girls? No, that's different. How many different ways can you reorganize the groups? Well, there's 3 groups, so 3 factorial. So you put that all into the calculator, you get 8,640. So again, the hardest part about all of this is if it's multiplying or adding. If you're doing different events, you're adding. If you're doing this all within one event, you're multiplying. All right, so what is sample space? Sample space is a list of all possible outcomes. Like, for example, if you're tossing a coin 3 times, you're not tossing up 3 coins at one time, you're tossing one at a time. So you flip a coin and record its outcome. So, like heads for the first one, then flip it again, get heads again, and then flip it a 3rd time, get heads. Or you can get all tails. Or you can get one head, but that one head could be head, tails, tails, or tails, head, tails, or tails, tails, head. Same thing with tails. So there are 8 different possibilities. A good way to know that there are 8 is because each coin has 2 sides. So for the first time you flip it, it's 2. Second time is 2. Third time is 2, so it's 2 times 2 times 2. So 8. What if you're rolling a die and adding up all the dots? Well, a standard die, you should know, has 6 sides. So if you add them all up, you get 36 different possibilities, and they're all listed here. So a sample space can be rewritten as a list, a table, a grid like this, or you could use Venn diagrams and tree diagrams to show every different possibility. There will be things in probability that you need to know as kind of common knowledge, like 52 cards in a deck of cards, 26 letters in the English alphabet. There are 10 digits. That means you have numbers 0, 1, 2, 3, all the way to 9. So a couple of things that you should know. A more common problem that a lot of probability questions ask is these random marbles in a bag, or in this case, a basket. So we have 3 green, 4 yellow, and 5 blue. That means there are a total of 12 marbles in the basket. So probability goes from 0 to 1, or 0% to 100%. There's no way of having probability that's negative or more than 100% or more than 1. Probability is a part over the whole, or the total. So like, for example, there are 3 green tickets out of the total 12 tickets. And any fraction that you have, you should always reduce it. So this is 1/4. This is theoretical probability. So in theory, if you go into this basket 4 different times, 1 out of those times you should get a green marble. There are things called experimental probability that people actually conduct experiments to do the numbers and get the numbers, but that's that. What about green or yellow? Well, there are 3 green, 4 yellow, so a total of 7 marbles that are either green or yellow out of the 12. And that's it. What about an orange ticket? Well, there are no orange tickets. And I've been saying marbles, huh? But there's no way of getting an orange ticket, orange marble, whatever we're talking about here. So the probability is 0. Well, what is the probability of getting green, yellow, or blue? Well, that's all of the kind of colors that we have here. So that's 12 out of 12, or 1. So 0 means that it never happens. 1 means that it always happens. Now, there are going to be some tricky questions out there that you kind of have to think about. So what about if you have tickets that consist of 5 digits? So that means the smallest ticket possible is 0, 0, 0, 0, 0. The last ticket that you can have is 9, 9, 9, 9, 9. And then you have all the tickets in between. So what is the probability that at random, a ticket consists of 5 different digits? Well, then you have to ask yourself, okay, well, it's going to be a probability, so I need to figure out how many tickets have 5 different digits. And you don't want to list them all out because that's going to be a lot. There's going to be 30,240, spoiler alert. But how can I count all of that without counting the 30,240 tickets? Well, you have to think about, is it a permutation or a combination? Well, there's a first number, there's a last number, there's a middle number, second, fourth number. So there are very specific places for these numbers to go. So that means it's a permutation. Well, there are 10 digits to choose from, and you want 5 of them. So that's how many tickets are. If you put that in the calculator, you get that 30,240. But how many tickets are there? Well, if you're starting from 00000 to 99999, well, there's 10 digits, 5 different spots. So each spot has 10 different possibilities. So 10 times 10 times 10 times 10 times 10, or 10 to the 5th, or 10,000 different tickets. So if you put that in the calculator, and some of y'all I've found out don't know about math enter. If you put in 30,240 divided by 10,000, press math enter into the calculator, it will give you the most reduced fraction. What about if you have a coin purse? This is another typical probability question. You have a coin purse that contains 2 pennies, 8 nickels, and 7 dimes. Find the probability that at least 2 of the coins are dimes in any order. So I'm going to introduce you to some notation. So P parentheses, almost like f of x, at least 2 dimes is a way for us to use notation to write this is the probability of at least 2 dimes. Well, at least 2 dimes means exactly 2 dimes, or exactly 3 dimes. So again, the hardest part about probability and counting and all that is, do I multiply or do I add? So you ask yourself the question, can I get exactly 2 dimes and exactly 3 dimes at the exact same time? You can. So these are going to be 2 separate events, so we're going to add them. So how do I figure out how many different ways for us to get exactly 2 dimes? Well, I'm not saying that you're pulling a coin out and stating exactly what it is first, and then so on and so forth. So the order doesn't matter. I can pull out dime, dime, penny, and that's the same thing as having penny, dime, dime. So the counting, the order doesn't matter. So how do I count these? Well, like I said, order doesn't matter, so it's going to be a combination. So let's count how many ways that we can get 2 dimes. Well, there are 7 dimes in the bag, so I want 2 of them exactly. Then I don't want a dime. I want something that's either a penny or a nickel. Well, there are 2 pennies and 8 nickels, so 10 coins are not dimes, and I want 1 of them. Now, again, I want a situation where I am pulling 2 dimes exactly and 1 penny or nickel. This is one event, so I'm going to multiply those two. Well, how do I find out the total number of ways of pulling 3 coins? Well, there are 17 coins, and I want 3 of them, and the order doesn't matter, so I'm going to do that as a combination. Then I do the same thing, but for 3 dimes. Well, again, the order doesn't matter. I can pull 1 dime and another dime and a third dime, and then like that same situation is like having the third dime first and the first dime last, and the same thing. So the order doesn't matter. So I have 7 dimes, and I want 3 of them exactly. The total number of ways of pulling 3 coins out of this purse is 17 out of 3. So if you do that in the calculator, you end up getting 49 out of 136. So why was the last problem a permutation while this one was a combination? Well, the last problem we're talking about tickets with digits in their spots. So ticket 00001 is different than ticket 00010. And then if you move that 1 anywhere else, it's still a different ticket. It's a different number. It's like ticket 1, ticket 10, ticket 100, 1,000, and 10,000. They're all different tickets, no matter that they're all the same ones and zeros, but it's still a different ticket. So it is very specific. Um, and then with this one, dime, dime, penny, and penny, dime, dime is the same situation. So order didn't matter there, so we did those using combinations. Well, what does it mean to be a complementary event? Well, either something happens or it doesn't happen. The probability that it happens and the probability it doesn't happen should add up to 1. That's what this little apostrophe means, is not. So from 6 women and 6 men, 5 people are chosen for a committee. Find the probability that at least one of those people that are chosen in that 5-person committee is a woman. So we're trying to figure out the probability of having a committee of at least 1 woman. All right, so that means that I would have 1 woman and 4 men, or 2 women and 3 men, or 3 women and 2 men, or 4 women and 1 man, or a committee of all women. That's like 5 different possibilities. So you could do the math for all 5 of those, or you can think about what's the complement event. Well, if you're looking for the probability that something happens, you can do 1 minus the probability it doesn't happen. So what's the situation where you're not having at least 1 woman? Well, that would be the probability that you have no women in a committee. Or you can think about this as the probability of having a committee of all men. So let's figure out the probability of having a committee of all men, because it's just easier to think about than a committee of no women. Well, how many men are there? Well, there's 6, and you want 5 of them, because that's the committee. So then I ask myself the questions like, okay, am I being very general about this or very specific? Am I putting these men in a specific office in this committee? No, I just want 5 men in this committee. If you labeled all 6 of these men 1 through 6, the committee with 1, 2, 3, 4, 5 will be the same committee as having 5, 4, 3, 2, 1. So the order doesn't matter. So this is a combination. But then you have to be careful of what's the total number of committees here? Well, how many total people do I have? Well, 12. And again, I'm not putting them in specific offices, so it's a combination, 5. So you end up doing the math and do 1 minus that, and you end up getting 131 out of 132 different committees would have at least 1 woman. That means on the complement event would have been that 1 out of 132 committees is a committee of all men. So again, complementary events kind of minimize the amount of work. I only had to do one probability, and I subtracted it from 1 to get the sum of all the other 5 different committees that could have been made with at least one woman. What else do we have about probability? Well, we have independent events. Independent events are events that where one happens, it does not affect the probability of another. Like if I roll a die and select a card from a deck of cards, does one affect the probability of the other? No. So the probability of A or B happening is the probability of A times the probability of B, just like we're doing one event. So we're multiplying the probabilities. It's multiplication. It's in one single event. Like, for example, this bag of marbles, this time it's marbles, not tickets, and somebody pulls out a marble, but then they put it back. That's the important part here. If they put the marble back in the bag, they didn't change anything. It's, you try to grab one without looking, it doesn't change anything. All the marbles are back in the bag, all the colors that you started with, all that. So that's what makes this an independent event. The probability of you getting a yellow first, which would be, well, there's 2 yellow, wrong color, wrong pen. So 2 out of how many total marbles we have here? 6. Then you put it back. Well, then you ask yourself the question, okay, well, how many yellow marbles are in the bag? Well, 2, because you put it back out of the 6. So 2 6 times 2 6, or 4 over 36, or 1/9. So that's a probability. That's independent events. It's usually whenever we put something back or we talk about 2 separate things that one doesn't affect the probability of the other. Dependent events are the opposite. That means that when you do something, it affects the probability of the other. Like, for example, in this problem here, we are not putting the marble back. So what's the probability of now getting 2 yellow marbles out of this situation? Well, all the marbles are there. Theoretically, there are 2 yellow marbles out of the 6 in the bag, but this person didn't put it back. They kept that yellow marble. So that means there's only 1 yellow marble left out of how many marbles are in the bag now if we kept one? 5. So this would be 2 out of 30 or 1/15. What about if you want to get the probability of at least 1 red? Well, you have to be careful with this because you're pulling 2 marbles out. Getting the red first and a yellow is different than getting a yellow and a red. And then a red and a green, or a green and a red are the same event. And then you have to think about red, red. Or make your life a little easier. If you're trying to get at least 1 red, we could do the complement event, which is 1 minus the probability of no reds. So what is the probability of getting no reds? Well, there are 3 marbles, yellow or green, that are not red. So 3 out of the 6. But remember that we're not replacing it. So that means that, well, if I took one of those non-red ones, I only have 2 marbles that are not red out of 5 marbles that are in the bag. So that would make it, the probability of not getting a red is 1 out of 5. So the complement event would be 4 out of 5. So the probability something happens, the probability something doesn't happen. All right, so sometimes it's nice to be visual about certain questions just so that you can see all the different possibilities. And again, this is something that we can do with sample spaces. Sample spaces can be tree diagrams. So I drew a tree diagram here where we have Carl here that has a car and a motorbike, but they're not very reliable. His car can only start 80% of the time. So I've made a variable C. Well, the C apostrophe means that the car doesn't work. Then he has a motorbike. That only works 60% of the time. And so I created a tree diagram with M and M prime, or not M, in probability notation. So what I'm going to do is I'm going to write the probability of each event happening on their little branches. So Carl goes up to his car. 80% of the time it works. So I'm going to make that a fraction, so 4/5. You can leave it as a percentage or make it a decimal if you want to. Well, the complement event is that, well, 4/5 of the time the car doesn't work. That means it doesn't work 1/5 of the time. So it works 4 out of 5 times. 1 out of 5 times it doesn't. The motorbike is 60% of the time, or 3/5. Well, if it works 3/5 of the time, it doesn't work 2/5 of the time. So same thing down here. Now, why are these probabilities the same as, the one above or anything like that? Well, they don't talk to each other. The car and the motorbike, if one works and the other one doesn't, or they both work, it doesn't affect the probability of the other. So these are independent events. So what I'm going to do is for each scenario here, I'm going to figure out the probability of it happening. Like if I multiply 4/5 and 3/5, you get 12/25. If you multiply 4/5 and 2/5, you end up getting 8/25. If you multiply 1/5 and 3/5, you get 3/25. And then 1/5 times 2/5 is 2/5, or 2/25. Now, these are only the 4 scenarios that can happen. So if you were to add up all of those probabilities that we did at the end, you end up getting 1, because that's all the different possibilities. All the different possibilities that can happen should all add up to 1. But there's multiple events that can happen. There are 4 different ways that the car and a motorbike work. So if I ask you what's the probability that they both will start, well, you go to the branch where you have C and M, and you get 12/25. That's the answer. What's the probability that he can only use a car? Well, that means if the car works, the motorbike doesn't work. He doesn't have an option. He has to use the vehicle. So if you go to the branches of the car working and the motorbike not working, you end up getting 8/25. So this is a way to see every single scenario. What if you have 2 boxes with 6 petunia plants in each of the boxes? However, box A only has 2 of those plants that are purple and 4 of them that are white. Box B has 5 of them that were purple and 1 that are white. So what I need to do is I need to go through the probabilities of each. Well, did it talk about how we select box A and B? Oh, you flip a coin. So like if you say heads is A and tails are B, so that means that there's a 1 out of 2 chance of getting box A and a 1 out of 2 chance of picking box B. Well, then if I think about in box A, there are 2 plants that are purple out of 6 in the box, so 2 out of 6 are 1/3. That means that there are 2 out of 3 that are white, or 4 out of 6 if you didn't reduce it. In box B, you have 5 that are purple out of the 6, and 1 of them that are white. So do that. So just for the sake of it, I'm just going to do all the multiplication, because the probability of getting one of these plants is not affecting the probability of choosing box A and B. So we're just multiplying the branches. So 1/2 and 1/3 multiplied to 1/6. 1/2 and 2/3 multiplied to 1/3. 1/2 and 5/6 is 5/12. And then 1/2 times 1/6 is 1/12. So again, if you add all those up, those are the only possibilities that can happen in this scenario, so they should all add up to 1. So what's the probability of getting a purple petunia plant or whatever we're doing here? Well, if we go through box A and get a purple plant, that's a probability of 1/6. If we go through box B and get a purple petunia plant, we get 5/12. So again, like I keep talking about, the hardest part about this is if it's adding or subtracting. Can I go through box A and get a purple and go through box B and get a purple? No. They are 2 separate events. So since there are 2 separate events, I'm going to add these probabilities together and get 7/12. You're only going through one box, and it says it. You go through a box and get a plant. You don't go through both. Another way of doing sample spaces is Venn diagrams. So here are some examples of what its shading looks like. So if I say we have this universe, this box, and we have A that's inside of this box, this is what it looks like. Well, what if I say it's not A? Well, it's everything in the box, but not in A. What is this upside down U thing here? Well, this is AND. What do they have in common? Well, the overlap. So that's why that's shaded. This U-shaped thing or union is the OR. What's in A or in B? Well, you shade everything in A or everything in B. So sometimes we will ask you questions about finding the number of things that are in a certain scenario. Later on, we'll talk about probability. So how do we determine the number of people that are in the club? Well, all of this universe is the people in the club. We have tennis players, we have hockey players, and then there's 7 out here that's neither a tennis player or a hockey player. So then if I were to add all of those numbers up, the 7, the 15, the 27, and the 26, you end up getting that there are 75 total people in this club. Well, how many play hockey? Well, it didn't say only hockey, it just says hockey. So there are 27 that play tennis and hockey, 26 that only play hockey, so 53 total people play hockey. How many play both sports? That's easy, that's the overlap. So 27. Who plays at least one sport? Well, that means it's the people that are playing only tennis, only hockey, or both. So 68. That's the OR. They either play tennis or hockey. They play only tennis, only hockey, or both. So you add up everything that's in the circles. Who plays neither sport? Well, it's the people that are outside of the circle but still in the universe. All right. So what do we have here? We have a set A that are all the factors of 24. Factors means that it's all the numbers that multiply to 24. So those numbers are 1, 2, 3, 4, 6, 8, 12, and 24. B are all the factors of 28. So that's 1, 2, 4, 7, 14, and 28. The word factor means the numbers that multiply to that number. It's like 1 times 24, 2 times 12, and so on and so forth. If it said multiples of 24 and multiples of 28, that's different. Those would be like 24 times 1, 24 times 2, 24 times 3. But factors are the numbers that multiply that. The universal set of integers that we're talking about are 1 and 28 inclusively. So that means we're talking about 1, 2, 3, 4, all the way to 28, including 1 and 28. So there are certain people that do this differently. Some people, when they draw a Venn diagram here, they write out all the different numbers that could be in there. So kind of like what you do in history or English when you do Venn diagrams, you list out what they have in common. Here, I'm going to kind of use this as probability, so I need to know the number of things that are in each of them. So like if you think about the smallest set possible, which is the overlap, how many numbers do they have in common? Well, 3. Well, in set A, there are 8 numbers. 3 of them are also in B, so how many are just in A? 5. B has 6 numbers inside of it, but 3 are also in A, so how many are not in A but in B? So 3. Well, that adds up to 11. Well, there's how many numbers in our universe? Well, 1 through 28 is 28 numbers. So if I have 11 of them already, I get 17 that are not factors of 24 and 28. So what is part A asking for? It's asking to find A and B, the set of A and B. So we're looking for the numbers that they have in common. So 1, 2, and 4. But what if I wanted to know how many numbers there are in A or B? Well, that's a different notation. That's this notation. The number of items in A or B would be 3. There are 3 numbers that A and B have in common. But finding A and B is listing out everything they have in common. So how does knowing the number of things inside help? Well, the probability of getting a number at random that's A and B is 3 out of the total 28 numbers. What's the probability of getting A or B? Well, if you look at the Venn diagram, if you add up all the numbers inside the circle, that's 11 numbers that are in A or in B out of the 28 total numbers. So those are two different ways that we can do Venn diagrams. We can ask you for the number, we can ask you for the probability. So let's practice some more probability. In a class of 30 students, 19 study physics, 17 study chemistry, and 15 study both. So I'm going to go over here and make a P here for physics, a C here for chemistry. And so the easiest thing to fill out here is that we have 15 that are in both. But they said that 19 were in physics altogether, so how many are just doing physics? 4. Well, they told us that 17 are studying chemistry, but 15 are doing both, so how many are just doing chemistry? Oh, that doesn't look like 30. That's only 4 plus 15 plus 2, it's 21. There's supposed to be 30 students in this kind of survey class thing that we're talking about. So that means 9 people are neither taking physics or chemistry, but they were part of this study or something. So I bolded and underlined it here, but it's up to you to figure out what am I asking for? Because if you don't give me probability, you're getting it wrong. So if we select one student at random, there are 15 students that study both subjects out of the 30 and always reduce, so 1/2. At least one subject means that they're doing physics or chemistry, so we add up all the numbers inside the circles and get 21 out of 30, or 7/10. How many people are doing physics but not chemistry, or just physics? That's 4 out of 30, or 2/15. How many of them are doing exactly one subject? So that means that they're only doing physics or only doing chemistry. That's 6 out of 30. And then neither subject, we found out that was 9 out of 30, or 3 out of 10. So that was tree diagrams and Venn diagrams.